Hello, everyone. Welcome to the Statistics in Medical Research tutorials. Today, we are going to look at regression analysis, and we'll be looking at the basic concept. This is the first episode in the series of lectures on regression analysis. So I welcome you to stay tuned and do well to go through all the different episodes so that you can have a comprehensive grasp of what regression model is all about, especially when applied to medical research. My name is Greg Okobo. Today, we are going to describe the concept of regression analysis in statistics. We'll find a way to think of and use regression model. We appreciate the purpose of regression in medical research and demonstrate the concept of the line of best fit as well as the regression equation. And finally, we'll attempt to derive the parameters of the regression equation. So let's go right into today's episode. We can define regression analysis as a statistical process for estimating the relationship between a dependent variable, otherwise known as the outcome, and the independent variable, also known as the exposure or the predictor. So what regression tries to do is to attempt to explain the relationship between an outcome and an exposure in a research using statistical means. And this episode is trying to look at the basics of what it's all about, and then look at the mechanics and the mathematics underlying this regression modeling tool. Before we go on, it's important that we appreciate what is a dependent variable and what is an independent variable. For example, in the relationship between cigarette smoking and lung cancer, cigarette smoking is the independent variable or the exposure, and lung cancer is a dependent variable or the outcome. Given that an individual smokes cigarettes, then the chances that that same individual will develop lung cancer is higher. So here, being exposed to cigarette smoking is a determinant of lung cancer. And throughout the regression process and modeling, it's always important that we are able to identify what the dependent variable is and what the independent variable is or are, because it can be one or more. There are other instances or research questions in medical research where regression modeling could apply. An example is the association between age and cardiovascular disease. Here, age can pass as the independent variable and cardiovascular disease as the dependent variable or the outcome. Another example is the assessment of the determinant of monkeypox disease. Monkeypox disease, in this case, is the dependent variable, and determinants will form the independent variable. Also, in a study of the effects of oral contraceptive pills on incidence of breast cancer in this case will be the outcome or the dependent variable, and the OCPs will be the independent variable. Another example is the predictor of time to readmission following chemotherapy for cervical cancer. Predictors here will serve as the independent variable, and time to readmission will serve as the outcome or the dependent variable. Lastly, if we look at a study with a research question on lung function and respiratory health of populations living close to quarry sites, lung function in this case, as well as respiratory health, will be the outcome variable or the dependent variable, and the populations living to quarry sites will be the independent variable. So these are some of the few examples. Many more research questions abound in the clinical sphere, and it's important that in all of the research questions that we come up with, we are able at the very beginning to identify what our outcome or dependent variable is, and then what are the independent variables or the exposures. It's also important for us to know exactly when to use regression in medical research. And this has to do with the analysis process. In medical research, the first thing to do is to collect the data, clean the data, and code it into any software that we are familiar with, like the SPSS, Stata, SAS, or R. After that is done, it's important that we begin to explore the variables in our data sets, and we understand how they are distributed, and then look for measures of location or dispersion. This will help us to appreciate and understand our variables and also help us to build the regression model. The next thing is for us to carry out bivariate analysis that will help us to link the outcomes with the exposures. This outcome or the dependent variable associating with the independent variable is a first step in regression modeling. Because one of the assumptions is that for variables to be regressed, there's an assumption that they are associated. So bivariate analysis help us to establish if two variables are associated and if they can go into a regression model. The multivariate or multivariable analysis is exactly the point where regression modeling is done. And at this stage, it is used to either identify significant predictors of our outcome or dependent variable, or to control for confounding variables, which are third variables that distort the association between primary exposure or independent variable and the outcome. This is exactly the point where regression model comes in medical research. So at what point do we think of regression modeling? When exactly should it cross your mind in the research process that you may have to carry out a regression modeling? Well, the answer is simple. If you focused on the steps involved in research, thinking of regression modeling is at the very beginning. When we conceptualize the research questions or topic, we need to think of regression model. This is important because at that point, it will help us to identify the outcome on the dependent variable, the independent variable, and any other variable that we may need to put into consideration in the research process. So regression modeling comes in at that very point and helps to tie up the analysis process. Another point is at the time when we have to measure or decide on how to measure the variables in our research. It's also important that we think of regression modeling, because the way we measure the variables and the level of data that we place the values of the variables is very important in determining the type of regression model that we'll carry out. And lastly, at the analysis state, we've already stated it earlier, that at the multivariate analysis level, regression model, if needed, is done. So these are the different points where we need to think deep about regression in the course of our research. Regression can be done for so many reasons in medical research, but here I've listed 4. The first is for prediction and forecasting, which is actually the major reason for modeling a regression in medical research. However, we can also use regression to estimate the probability of an outcome, given some sets of independent variables. We can also use regression model to identify independent predictors of an outcome. But most importantly, regression is needed to infer causality or to infer causal relationship between the independent variable and the dependent variable, especially in instances where the research question is either etiologic or interventional in nature. At that point, it is important that we adjust for confounding variables in our research, and regression model comes in handy. So let's talk about the basic mechanics of regression analysis. These are things that we have to pay attention to that are rooted in the maths of regression model. Top on the list is the line of best fit, which will also lead us to the regression equation. And then lastly, it will help us to differentiate between correlation and regression. To do this, we'll take a working example. In this example, we are going to look at the association between weight and packed cell volume among adults participating in a statistic course. The investigator randomly selected 5 participants to answer the research question bordering on the association between weight in kilogram and PCV in percent. So the first individual participant has a weight of 58 kg with a PCV of 40%. Second individual has 64 kg and a PCV of 46%. The third, 60 kg, PCV of 44%. The fourth, 70 kg, PCV of 49%. And the fifth, 45 kg with a PCV of 41%. Having measured both the weight and the PCV, the next step for us is to plot these values using a scatter diagram. This will help us to describe the relationship between weight and PCV. In the scatter diagram, weight is the independent variable and plotted on the x-axis, and PCV is a dependent variable or the outcome, and is plotted on the y-axis. So the first individual with a weight of 58 kg and a PCV of 40% will appear on that dot on the graph. The second individual here, third here, fourth, and then fifth. If you look at this graph closely, it appears that weight and PCV have some sort of a linear relationship. With weight increasing, PCV also increase. This relationship can be best described as correlation, and correlation describes the association between the weight and PCV in terms of the direction of the association and in terms of magnitude. So if we know the direction and the magnitude, we can describe the correlation between weight and PCV. Now for this example, the correlation coefficient is plus 0.82, which simply means that the relationship is in the positive direction, represented by the plus sign, and it is strongly positively correlated, as represented by the magnitude, the value 0.82. Correlation coefficients range between 0, -1, and +1. +1 indicates perfect positive correlation, and -1 indicates perfect negative correlation. In this case, this is almost a near perfect positive correlation. So now that we can agree that there is a relationship between weight and PCV, can we use weight to predict PCV? And to answer that question, we need to put a line that best describes the data points. This line that best describes this data point is referred to as the line of best fit. It's a straight line that approximates the given set of data in the scatter plots. And this particular line is drawn so that we can predict the outcome variable given the independent variable. This is one of the reasons why we model a regression. And that is why for us to draw this line, a regression model comes in. So the regression model simply helps us to draw the line of best fit. However, this line of best fit is described mathematically by an equation. Y equals to beta naught plus beta 1 xi plus e. We are going to describe what all these terms and parameters mean. But it's important for us to know at this stage that the line of best fit is described by this equation. And this equation which is known as a regression equation, is the hallmark of regression modeling. So our ability to find out the values for beta naught and beta 1 and describe this equation is what regression model is all about. So let's see if we'll be able to describe this line using this equation. For us to do that, there are methods that have been developed by mathematicians and statisticians. And these methods, I'm just mentioning two here. There are others: the ordinary least square method, the OLS, or the maximum likelihood estimation method, the MLE. So either of this method will help us to describe the line of best fit, or rather fit a line to this data in such a way that this line will represent the best approximation of all the data points. So this equation we have here simply describes this line. It represents this line. So let's look at this equation closely to understand what every aspect of it means. The y in this equation is a dependent variable or the outcome in the study or in the research that is being predicted. Now, this outcome in our case will be the PCV. So everything to the left is this outcome, and that outcome actually describes that line of best fit. Everything to the right, on the other hand, describes also that same line. So both the left and the right describes the line of best fit. For us to describe this line, we need to understand these parameters in this equation. So we are going to start with beta naught and understand what it means. Beta naught is the mean value of y when x is 0. X here simply means the independent variable. So if weight in our example is 0, what is PCV? Simply put. And statisticians have been able to come up with a formula to compute beta naught using the sets of data that we have collected from the field, from our study. With those data, we can compute beta naught, and then one of the parameters of the equation is provided for. The next parameter is beta 1. Beta 1 is the slope or the regression coefficient. And this simply means the mean change in y for a unit change in x. X here is the independent variable. If x changes by just 1 unit, how will y respond? That's exactly what beta 1 represents. In our case, this will simply mean if weight increases from 60 kg to 61 kg, just 1 unit increase, by how much will PCV increase on average? So this is exactly what beta 1 represents. And just like beta naught, it has a formula developed by statisticians. We are not interested in this formula for now, but rather we're interested in actually knowing how to interpret the meaning and give meaning to beta 1. And just in case you've not noticed, beta 1 and beta naught are actually referring to y. They are mean values of y, even though they are on the right side of this equation. The next item on this equation is x. X is the independent variable that have impact on the dependent variable y. And this independent variable in our example is weight. So which we observe from the study, the values we measure from the study. So x is very important in the regression equation because that's exactly the independent variable we are interested in building a relationship and finding out how it affects the outcome, which is y. The last term in this equation is the random error term, otherwise known as the residual. This is just simply the difference between the observed and the predicted values of y. The following example will help to elaborate more on what the residual or the random error term means in regression equation. However, it is also important that we note that a lot of the regression assumptions that we make depends on this residual. And these regression assumptions, they are guesses about how the distribution that gave rise to our sample is functioning. And this guess needs to be tested and confirmed before we can conclude that this equation is valid. So for us to do that, we need to find meaning to the residual, as well as all the assumptions made around the residual. In the next episode, we'll be looking at regression assumptions as well as the R squared. So I encourage everyone to please listen and go through that video. So let's look at how we derive the values of the regression equation. Still using the examples earlier stated of the 5 participants randomly selected to look at the relationship between weight and PCV. We are going to describe that using a cross tabulation, just a table. And in this table, the observed weight, which is X in this case in the equation, will be on the second column. And the observed PCV or Y will be on the third column. So given these two from our study, which we have observed for our participants, we calculated the regression equation. And if you take a look at this regression equation, which we have, is very, very similar to the regression equation we've already explained. So in this equation, 24.8, which is beta naught, simply means if X, which is the independent variable, is 0, what is Y? Y will be 24.8%. And remember, Y is PCV. The 0.32, on the other hand, is beta 1, which simply means if we increase X, which is weight, by 1 unit, in this case 1 kilogram, by how much will Y increase, or by how much will Y change? And here it is 0.32%. So the PCV will increase by 0.32% by 1 unit change or 1 unit increase in the weight of the participant. And of course, the regression equation is not complete without the residual error, which in this case is 0. In a well-modeled regression, the residual error is 0 on average. So if it's not 0, then we may have to reconsider the regression equation. Something is wrong somewhere. So most times you will see this equation without the residual indicated because it is 0. And how do we actually calculate this residual error? We do that by simply taking the observed independent variable, in this case, the weight, and then one after the other, putting the data points into the equation and using that to predict a possible PCV. If we do that for all the 5 data points, we'll get these predicted values of the PCV. So for an individual, the first individual here that has 44% PCV, the equation predicted that this individual on average should have 44.19%. So you notice quickly that there is a difference between the predicted PCV and the observed PCV. That difference is the residual or the random error term. And if you take the mean of this random error term, should be 0, as we've earlier postulated. So if we have an individual now who weighs 65 kg, what will be the predicted PCV? 45.6%. So this is the beauty of the regression equation or the regression model. I must warn at this point that prediction using the regression equation should not exceed the range of values of the independent variable. If it does, there will be a lot of noise and uncertainty in the estimate of the predicted outcome. So that's why 65 in this example is within the range of values of our study participants that we've used to develop the regression equation and then to predict the outcome. So at this point, I want to thank every one of you for listening, and please stay tuned for the next tutorial, which will focus on regression assumptions and the R squared and what it actually means.